racing at the end to try to get through everything. And this kind of stuff takes time to kind of process of where does we even are. Please try to stay kind of caught up with the homework. Do a few problems from each of the sections as you go through them, just for the practice as you do this. So let me go and walk through this. Geometric series. Geometric series only applies when it is a geometric, when we have a geometric actual series, meaning we have a common ratio R. Common ratio is obtained by dividing the one term divided by the previous term. And that will give you the common ratio. As long as that common ratio is less than 1, or I should say the absolute value of that common ratio is less than 1, then it's going to be convergent. This one actually converges to a specific value if it converges. It converges to A, the first term, over 1 minus R, the common ratio. We use that to also do the repeating decimal. So we did that earlier today. Geometric series can sometimes be negative. In fact, it can even be alternating on occasion. And still be convergent. If it's not less, if absolute value of R is not less than 1, then it is divergent. Strictly less than 1. Telescoping we don't get too often. Telescoping, if it's telescopic, what's going to happen is everything's going to collapse down in between, and you're going to have some terms at the beginning and at the end, and then you got to run a limit. It's either going to be convergent or divergent based on that limit. Usually you have to write out quite a few terms to really kind of see the pattern. Test for divergence says, if the limit of your series does not go to 0, then the entire series is divergent. Now, this does not have a clause for meaning that it's automatically convergent or something like that. It just means it's inconclusive if that limit does not go to 0. I'm sorry, if that limit does go to 0, I should say. Integral test. There are 3 major axioms we need to have. First of all, we need to convert our a sub n into an f of x, meaning change it from a discrete to a continuous function. Using that continuous function as an analog for the discrete function, we can say we need to show that f of x is positive for all values of x bigger than 1. It is decreasing for all values of x bigger than 1. We may have to use a derivative test for that. It is positive, decreasing, and continuous for all values bigger than 1. Now, when I say 1, the problem may start at 7 or something. It doesn't matter where it starts, as long as it's following all those pieces. If those 3 axioms are held to, we're good to go. We can try the integral test. We set the integral from 1 to infinity. Excuse me. 1 to infinity, or a to infinity, wherever the beginning point is. If that integral is convergent, so is the series. If that integral is divergent, then so is the series. P-series is a special case of the integral test. P-series says if I have a summation of 1 over n, a changing base raised to a constant power. If I have that scenario, then in that case, it's depending on that exponent, if p, that exponent in the denominator, is bigger than 1, strictly bigger than 1, then it's going to be convergent. If it's anything other than bigger than 1, meaning if it's less than or equal to 1, it's going to be divergent. Next up, we have direct comparison. I don't like that one so much. Direct comparison says, first of all of your terms have to be positive, including the ones that you're, the series that you're comparing it to as well. If the series that you want to know is convergent or divergent, let me start here. If the series that I'm comparing it to, if that's convergent, and it's always bigger than the other, what I'm looking for, we're good. It's exactly opposite for the other. I try not to use that one too often. Limit comparison says, take what you, everything has to be positive, you have to cover all your bases. But then you can do the limit of what you want over what you're comparing it to. If that limit goes to a positive, specific, real number, then the fate of the one is the fate of the other. It's a good comparison. If the one you're comparing it to is divergent, so is what you're looking for. If it's convergent, so is what you're looking for. Alternating series test, one of the easier tests, like a geometric or a p-series, pretty easy to use. Alternating series test says if all of your terms are if you have an alternating series, meaning a -1 to a power, if all the terms are positive of the non-alternating part, if it's decreasing, and if the limit goes to 0. If all that holds, then it is convergent. This does not have a contingency if one of those axioms do not hold. If one of those axioms do not hold, almost for sure, you're going to go here. Test for divergence. Okay. I've never run into a scenario where that didn't work. Next time what we're going to have is we're going to have 2 more major tests and then sort of a third one that's sort of a nebulous one that covers all of them. Now last time what I did was I went through and highlighted which ones all the terms had to be positive. Integral was 1. All the terms have to be positive. P-series, again a special case, all the terms have to be positive. They are by nature, 1 over n raised to the p power. Direct comparison, one of the terms is one of the conditions is all the terms have to be positive. Same with limit comparison. How about alternating series? Overall, are all the terms always going to be positive? No. No, for sure no. In fact, if they are, it's not an alternating series. You can't use the test anyway. So this is going to be the main one that we're going to run into some trouble with for next time's lecture. Any questions? Just one more midterm, then a final.
3.
Oh. Sort of 3 more. Yeah, there's 2 specific ones with names, and then there's a third one that's not a test in itself. It just enhances some of your. I'll see you guys next time.